let me generalize this property to the case of fields which are not necessarily given as k of alpha. So now let me take an arbitrary finite extension of k. And let me define the separable degree as a number of possible homomorphisms of L into algebraic closure of K. Again, if L is generated by one element alpha, then this degree is just the number of distinct roots of its minimal polynomial. If L is k of alpha, then this is just the number of distinct roots of its minimal polynomial. And let me say that the extension L is separable over K if the separable degree is equal to the degree. And I can also define the degree of inseparability of L over K as the quotient, well, the degree divided by L over K separable. But this will be not very important in the sequel. So let me formulate a theorem. First part says that the separable degree is multiplicative. If I have L an extension of K and M an extension of L, then M over K separable is equal to M over L separable times L over K separable. And M is separable over K if and only if M is separable over L and L is separable over K. So this is part 1. Part 2 says that the following things are equivalent. 1. L is separable over K. 2. Any element of L is separable over K. 3. L is generated over K by a finite number of separable elements. And 4. L is generated over K by a finite number of elements, and each A alpha is separable over the preceding stuff, K alpha 1 and so on, alpha I minus 1. Remark, the same holds when we replace separability by pure inseparability. Okay, so let me give a proof of this theorem. Well, part 1. We know that any phi from L to K bar extends to f phi tilde from M to K bar. This is the extension theorem. And in fact, there are exactly M over L separable ways to do this. Since K bar is also L bar, since given phi, one considers K bar as L bar. An algebraic closure of K is also an algebraic closure of L once an embedding of L into K bar is given. Then the number of ways to extend is computed just by definition. By definition, it's the separable degree of M over L. Now, this implies the first part. Thus, we have M over K separable equal to a product of L over K separable M over L separable. Now, the equivalence of separability of M to the separability of M over L and of L over K. So equivalence of separability. This is just the inequality, in fact. Just the fact that the separable degree of an extension over K does not exceed the true degree. Okay? So if the separable degree and the degree are both multiplicative, and if one of them does not exceed another, then we can conclude everything. And this fact, now this is proved, the last fact is proved by induction using the fact that this is true for E generated by one element. Well, part 2. 1 implies 2. So 1 is L is separable over K, and 2 is any element of L is separable over K. This is the consequence of the first part. The first part implies that any subextension of a separable extension is separable. K of alpha over separable extension L is itself separable. Well, 2 implies 3. So if any element is separable over K, then L is generated by separable elements. It's clear. If any element is separable, then of course the generators are also separable. 3 implies 4. Well, if AI is separable over K, then AI is also separable over an extension of K. This is clear because the minimal polynomial of AI over K of A1 and so on, AI minus 1, divides the minimal polynomial of AI over K. We have seen this in the last lecture. And so if the big one is separable, that is to say, has distinct roots, so then the small one is also separable. If P min of AI over K is separable, which means that it has distinct roots, then so is its divisor P min of AI over K, A1 and so on, AI minus 1. And finally, 4 implies 1. Well, this can be proved by induction as above. I shall not give more details. So, one might ask, is the notion of separability defined for extensions which are not necessarily finite? Yes, in this case, it is best to define a separable extension as such extension that all its elements are separable. In particular, if L over K is not necessarily finite, and algebraic extension, we can define L separable. The separable closure of K and L as a set of all X such that X is separable over K. A separable element is by definition algebraic, of course, it has minimal polynomial. So the preceding theorem implies that this L separable is a subfield. L separable is a subextension called separable closure of K in L. Well, I think normally one presumes that L is algebraic. Okay, and of course, L is purely inseparable over L separable. Well, and finally, maybe I will repeat the important remark. If the characteristic of K is 0, then any extension is separable, and if characteristic of K is P, then a purely inseparable extension has degree P to the power R, and always this degree of inseparability is P to the power R.